This is a video on optimization problems. I've gotten these questions from Madass Maths. It's a website, I'll leave the link in the comments. I think there's around 40 questions for this optimization problems worksheet, and I won't go through all of them, but I'll have this as a series, so I'll have 3 parts to it. This will be the easiest part, so it's difficulty level 1, and then we'll go to medium in the next video, and the last video will be hard, and the last video will be the longest, because for the first video I'll only go through 4 questions, the 4 which I think are the hardest, and then I've just picked the first one as the easiest, just to go through something simple. The second video I'll go through 4 questions again, because that's just medium difficulty, and the last video I'll go through every single question on the hard difficulty one. Question 1. An open box is to be made out of a rectangular piece of card measuring 64 centimeters by 24 centimeters, which is here, so 64 by 24, figure 1. Figure 1 shows how a square of side length x is to be cut out of each corner so that the box can be made by folding, as shown in figure 2. Okay, so here we've got x, so this is a small square. What we've done is we've got this rectangle here. We're going to take out these squares here on either side, so we can fold it up like that. Okay, and by doing that we'll get this shape here, and we want to find the volume. Okay, well, first of all, the volume is going to be this multiplied by this multiplied by that. Now this length here, it's not going to be 24. It's going to be it's not going to be 64. Sorry, it's going to be 64 minus x here, minus this part, also minus x here. So it's 64 minus 2x for this length here. And then for here, it's going to be not 24. It's going to be 24 minus x, 24 minus another x. So it's 24 minus 2x here. Because remember, we've cut this part out, so we've got rid of this length here and this length here. And yeah, okay, so this is 64 minus 2x, 24 minus 2x, and this height here is just h, because this height is this one here, and that's equal to this. So 64 minus 2x multiplied by 24 minus 2x multiplied by x, expand that, you'll get this, as the question wants, for part A. Part B, show further that the stationary points of V occur when this is true. Okay, well, stationary points occur when the first derivative is equal to 0, okay, and that just means the gradient is equal to 0. Like, what value of x gives you a gradient which is equal to 0? So differentiate, you'll get 12x squared minus 352x plus 1536. To get this, remember stationary points occur when the first derivative is equal to 0, so when the gradient is equal to 0. So dv over dx is equal to 0. Divide by 4 to get this, like the question wants, and then find the value of x for which v is stationary. So we just want to solve this basically. I put it into a quadratic formula, I think, or just a calculator. Well, the question gives you a hint, so you can factorize this, but I couldn't be bothered, so I just put it into a calculator. I mean, you know how to solve a quadratic. You'll get x equals 16 over 3, or x equals 24. Now, x can't equal 24, because if you look at this, well, this length here is 24. So if x here equals 24, it's going to be as large as this width here. But that's just obviously not correct, because we can just inspect this and see that x clearly isn't 24. Whatever it is, it's less than 24. Okay? And x also can't be 12, because we'll have 12 here and 12 here. X can equal 16 over 3, because that's around 5.3 recurring. And 5.3 recurring is fair to have on both sides. So we have to assume that, well, we know that x equals 24 is incorrect, so we can only have this. Now we want the volume. Oh no, so that's part C done. We want to find the volume. We want to find the maximum value of V. Well, V is maximized when x equals 16 over 3. So plug this into your volume equation to get this. Put into a calculator if you want one, but you get 3,793 centimeters cubed. To prove that it's maximum or minimum values occur after you analyze what's actually going on at the second derivative. So we've got the first derivative as this, To determine the nature of this point here, to see that like whether it's maximum or minimum, whether it maximizes or minimizes v, we have to find the second derivative. So this, we want to find the second derivative, which is 2 multiplied by 12, which is 24x minus 352. So that's the second derivative. Plug your value for x into it to get that. You don't even need to like solve it. You might be able to just see that this is less than 0. And whenever the second derivative is less than 0, it's a maximum. So this is fine to say. Question 2. The figure above shows the design of a fruit juice carton with a capacity of 1,000 centimeters cubed. The design of the carton is that of a closed cuboid whose base measures x centimeters by 2x centimeters and its height is 8 centimeters. Okay, well, the volume is 1,000. You know that. The volume is also equal to x multiplied by 2x multiplied by h, so the volume is 2x squared h. So these are equal, so we'll just have that on the side there. Okay, we're looking for the area. Well, the area is going to be x multiplied by h. Okay, but we have 2xh, because if you look at this, we've got this face here, then we've got another one at the back, just on the other side. Okay, so you have 2xh plus, and then here we've got what was it? So we've got 2x multiplied by h, so we've got 2xh here again, and we've got that on both sides as well, because we've got this face here and the other one. So it's multiplied by 2xh multiplied by 2, so it's add 4xh. And then on the bottom we have x multiplied by 2x to get the bottom face. We've got 2 of them, remember, so multiply that by 2 to get this as the surface area. And if we rearrange this one for h, we can plug it into here. And the reason why we need to do this is because, well, the question wants the area in terms of x's, but we've got it in terms of x's and h's. So if you look at this, these are actually simultaneous equations. So if we rearrange this one for h and plug it into there, we can have it exactly how we want it. So 6 over 2 is 3 multiplied by this, and then it's just over x, because the x cancels with the x squared a bit. So it's 3,000 over x, add 4x squared, like the question wants, and then just swap these two around to get it like that. Find the value of x for which a is stationary. Okay, but remember, stationary points occur when the first derivative is equal to 0, so just differentiate this. If you don't know how to differentiate something like this, well, you just do 3,000 multiplied by x to the power of minus 1. So x is to the power of minus 1, and the reason why that's good is because now we can do 3,000 multiplied by minus 1, which is minus 3,000, and then reduce minus 1 by 1. So minus 1 take away 1 is minus 2. So it's minus 3,000 over x squared here, and obviously 4x squared just differentiates to 8x. So you have 8x minus 3,000 over x squared. Remember, stationary points occur when this is equal to 0, so just set it equal to 0. Add 3,000 over x squared to both sides, multiply by x squared, and then just solve for x. I'm sure you know how to do this, but x equals 5 cube root of 3. Plug this into your, what are we looking for? The area. So plug this into here, which we've just found, to get, because this value either maximizes or minimizes the area. So we'll plug it in and then we'll see what it does. You've got the area as this. Solve it to get 624 centimeters squared. Remember, we need the second derivative to work out its nature, whether it maximizes or minimizes a. So the second derivative is, well, ax differentiates to 8. 3,000 multiplied by x to the power of minus 2. Minus 2 multiplied by minus 3,000 is positive 6,000. And then minus 2 minus 1 is minus 3. So it's positive 6,000 x to the power of minus 3, or positive 6,000 over x cubed. And then you've got the 8 here. Like that. Plug your value for x into it, which is, remember, 5 cube root of 3. Solve it to get this, which is positive. And because it's positive, it's going to be a minimum. Because when the second derivative is larger than 0, you've got a minimum point. So x is therefore going to minimize a. Question 3. The figure above shows a solid brick in the shape of a cuboid measuring 5x by x by h. The total surface area of the bricks is 720. Okay, so the volume, we're looking for the volume in part here. So 5x multiplied by x multiplied by h, so you have 5x squared h is the volume. The area, we're told, is 720. So if we get an expression for the area, we can make it equal to 720, so we can solve these simultaneously. Well, not solve them necessarily, but just to rearrange V in terms of only x's. Okay, so the area here is 5x multiplied by h multiplied by 2. So you have 5xh, then you'll have 10xh, because you've got this face here, and then you've got the one behind it. Similarly here, you've got, 5x multiplied by x to get the bottom face. So you have 5x squared, but you actually have 10x squared because you have to add this one at the top here. So 5x squared multiplied by 2, which is 10x squared. And then you've got xh, which is this face here. Multiply that by 2, get the other face there. That's that. Simplify this. To get this, we want the area in terms of only x's. So if we, first of all, actually the surface, no, we want the volume only in terms of x's. We're told that the surface area is 720, so replace a with 720. Rearrange for h here, so 720. Actually, we can divide everything here by 2 to get 360 equals 5x squared plus 6xh. Take away 5x squared, divide by 6x to get h as this. Plug this into here, so then we'll get v only in terms of x's, like that. And now you can just distribute. So 360 multiplied by 5x squared is 1800x squared. Later on in the later parts, I'll go through more smarter ways of maybe doing this, so you don't actually have to think as much. But I won't go through that just right now, because I feel like it's overcomplicating it for, especially an example like this. So you get 1800x squared minus 25x to the power of 4 over 6x. X cancel, and 1800 over 6 is 300. So you'll have 300x, and then this is minus 25 over 6x cubed, like that, like the question wants. Find the value of x for when v is stationary. Well, stationary points occur when the first derivative is equal to 0. So differentiate this, you've got 300, and then it's minus 3 multiplied by 25 over 6. Actually, I'll just go through it now. So 3 multiplied by 25, just think about that, that's like one number, okay? But the 3 multiplied by 25 over 6, the 3 and the 6 cancel. So it's like saying a half multiplied by 25. That's 25 over 2. And then reduce this by 1. So you have 25 over 2x squared minus 25 over 2x squared, and you'll have 300 here. You'll get that. Set that equal to 0. Remember, stationary points occur when the first derivative is 0. Add 25 over 2x squared, multiply by 2, divide by 25, x squared equals 24, so x equals root 24 or 2 root 6. You don't want the negative solution, remember, because you can't have a negative length. You might just want to put that on the side here as a statement. So this value of x either minimizes or maximizes the volume. Let's see what it does. So let's plug it in to the volume here. Use a calculator if you want. You'll get 980 centimeters cubed, around that. Okay. We'll see what it does. So find the first derivative, which you've already got. Then the second derivative, because remember, the second derivative tells us whether it's a maximum point or a minimum point. And if x here is a maximum point, it's going to maximize our volume for v, sorry. But if it's a minimum point, it's going to minimize it. Okay, so we'll plug this into the second derivative. This tells us the nature. We'll get this. You don't even need to solve it. Not that it's that hard anyways, but you'll know that this is less than 0. And if it's less than 0, you've got a maximum point. So whenever the second derivative is less than 0, you've got a maximum point. Whenever it's larger than 0, you've got a minimum point. Question 4. The figure above shows a box in the shape of a cuboid with a rectangular base x centimeters by 4x centimeters and no top, and the height is h. It's given that the surface area is this. Okay, well the volume, a tip for these questions is, I don't know if I've already said it, but just always work out the volume and area. So the volume is 4x multiplied by x multiplied by h, so it's 4x squared h. The area is 4x multiplied by h, which is 4xh, but you've got two faces, so it's 8xh. And then you've got xh, add xh, so it's 2xh. And then you've got 4x multiplied by x, so it's 4x squared. You've only got one face here at the bottom. You don't have a top one because it has no top. Okay? You get this. simplify, make it equal to 1728 because that's the surface area that the question gives us. Okay, you can divide by 2 on both sides to get this, and then we want to just rearrange for h, so take away 2x squared, divide by 5 over x. You'll get that like the question wants. That's fine. Show that the volume is this. We want the volume only in terms of x's and not x and h. We've got what h equals in terms of x's, so we can just plug this into there to get this. And just think about this. So here the question, they've factorized it. So there's no point of us just distributing this entire thing across, because we're just going to end up with a massive number and it's just going to be annoying to work with. So what I'll do first is I'll just distribute the x squared. Okay, and I'll cancel it with the x at the bottom. So we'll have 864x minus 2x cubed. And what I'll do next is I'll just factorize the top. To get this, you can take out 2. And then I'll just distribute the 4 only across this to get that. And this is like saying 8 over 5 multiplied by 432x minus x cubed, which is what the question wants. And just think about that, because if the question has given it to you factorized, what's the point in expanding a big mess? You could just factorize it before you get to like the big factorization at the end. Anyways, you'll get this for the volume. Okay, v is stationary. Find the value of x which either minimizes or maximizes it. So remember, we want the first derivative to be equal to 0, so just expand this. Say differentiate first, so 300 this, because it's just x to the power of 1. 1 multiplied by this is just itself. 1 take away 1 is just 0. This becomes anything to the power of 0 is 1, so this just becomes 1 multiplied by this. So that's 3, 4, 5, 6 over 5. Here, this is minus 24 over 5 x squared. To get this, remember, stationary points occur when the first derivative is equal to 0. Set that equal to 0. Multiply by 5 on both sides, add 24 on both sides, divide by 24 to get x squared equals 144. So x equals just 12. Remember, take the principal root. The principal root means only to take the positive solution when you square root on both sides. And we're doing that because we know x cannot be negative, because you can't have a negative length. So x equals 12 either minimizes or maximizes v. Okay, we'll plug it into v, okay, just to get the answer. Just, put that into a calculator, you'll get this. Okay, now we want to find if this is the maximum or minimum value. Okay, so the way we do that, remember, we can find the nature of x using the second derivative. So we've got the first one here, and then the second one, well, this goes away. 2 multiplied by this is minus 48 over 5x. Plug our value for x in, x equals 12 if you remember, plug that in. You don't even need to solve it, but you know that this is going to be negative. Okay, I didn't actually bother solving it, but this is going to be negative, which is less than 0, therefore it's a maximum point. Okay, I'm just going to go over this part again because I don't think I went over it as clearly. We've solved for x by we found what value of x gives the gradient as 0. So remember, stationary points occur when the gradient is 0, so it's like a flat line across. Okay, so we've set this equal to 0. We've solved for x, which is 12. So when x equals 12 on the x-axis, somewhere, if we keep on going up, we'll find a stationary point. That's a horizontal line with a gradient of 0. Now, if you think about it, if it's a quadratic looking like this, okay, and the x is like 12 here, and if we go up, well, this is the top of the quadratic, so that's the largest point. Okay, and that largest value of x will give us the largest value for the volume. Okay, I hope that makes sense. So the value of x will give us that largest value of the volume. Now, the quadratic could also look like this, like a U shape. And, well, when you set the derivative equal to 0 and you find what the nature is, when x is, say, like 3, and if you keep on going down, that gives you the stationary point, but it's down here. Well, that tells you that's the minimum value for for the volume. Okay, so whatever this value of x either minimizes or maximizes the volume, depending on what the second derivative is. So this will tell you if it's going to be at the top or at the bottom. So if it's going to be maximum or minimum. Whenever this is less than 0, it's going to be a maximum. But whenever it's greater than 0, it's going to be a minimum. Okay, I hope that makes sense. That's the last question for the first part. And yeah, so I'll do parts 2 and 3 sometime over maybe next week. I'm not sure.